Okay, all right, folks on Zoom, can you hear me okay? Can I get a heck yeah?
Yeah, we can hear you.
All right, awesome, thank you. All right, stop my video, okay. Oh, let's get started. All right, so announcements first. Homework 5 is in Python. I did get around to writing a version of it in Python. It works with the autograder, should work with the autograder. There's been a lot of bugs with the autograder recently. So if you've been submitting, I encourage you to submit again. It should be all fixed now, but there is a version in Python if you want to use that. A few of you said you preferred doing it in Python. I am also changing the due date. I don't know if you guys have noticed for homework 5. So it's going to be due Friday at midnight. Okay. There's not going to be a homework 6 because your midterm is coming up. All right. So homework 5 is due Friday at midnight. There was a correction on quiz 5. So what I did is I gave everybody 10 points. Obviously, you can't go above 100. So if you figured out. So one of the questions in quiz 5 was asking about the running time of checking if an edge exists in the adjacency list representation. The answer key was wrong. The correct answer is it takes degree of V or degree of W, as we discussed. So I fixed the answer on the quiz, but a lot of you had already taken it. So I just gave everybody an extra 10 points. So whatever your score was, I plus 10. Okay. If it was 100, I'm sorry, you plus 10. 100 plus 10 equals 100. So yeah, cool. All right, next big announcement, you guys got to start preparing. So again, there is not going to be a homework release this week because we will be preparing for the midterm. I will try to release instead a study guide, but you guys have all the material. You've got slides, you've got lecture notes. So I encourage you to start studying. I will provide more details about the format of the midterm probably on Friday. So you guys are aware of exactly what it's going to be like. But it will be not this Friday, but next Friday. And the Wednesday before that, we're going to have a review lecture in class. So I will try to prepare a few questions that we can work through, similar to what might be on the midterm. But I encourage you guys to come prepared with sort of like questions or things you don't understand. Basically, anything we've covered up to Monday might be on the midterm. So just keep that in mind. That makes sense? Cool. All right, other reminder, on Piazza, there's a post that links to the meta survey. There's a link here as well. So this is how I get graded. I guess you could say this is my midterm. So you could, if you can, please fill this out. Just a reminder, it does not affect your grade. I actually don't even know. I don't know if we collect email addresses, but I am not running the form. Our TA, she is running the form. So I don't know who you are. So if you want to like give me a bad grade, that's fine. I will not know. And even if I did know, it would not affect your grade in this class. All right, just to clarify. Cool. It's going to be open until March 11th, which kind of overlaps with your spring break. So I just encourage you to like get it done earlier if you can, because you're definitely going to forget if you try to do it, you know, March 11th, because that's going to be middle of your spring break. Like you're not going to be thinking, I don't want you to be thinking about school. Cool. All right, any questions on the announcements? All right, so what I do know is the midterm is definitely going to be like on paper, in person, in class, in this classroom. So everybody that joins on Zoom, you need to plan to be here that Friday in person to receive your exam. Just make sure you guys heard me. If you have any friends in the class that usually don't come to lecture because they join on Zoom or something, like remind them the midterm is on Friday. They need to be here. I'll try to send out an email. I'll try to remind them as well. All right. Cool. How are we feeling? All right, let's get started. So today we're going to cover breadth first search. All right. So basically what we were covering before, what we covered last lecture was depth first search over the last 2 lectures, right? So if you remember in your head, depth first search is this idea that you're exploring a maze. You kind of have a little string that you're holding on to, and you're trying to go as deep as possible first. And only when you run out of on your string and you start, you know, you kind of like search, where else can I go, right? So there is another method for exploring a graph, which is more to maybe like how you would do it if you could fly, for example. So imagine you could fly and you have an aerial view of the graph. This is how you would explore it. So again, yeah, I don't know why this keeps happening. This thing should be here. Anyway, what we're gonna do is we're gonna keep track of a state within each of our vertices. These are gonna be our different states, okay? Just for the purposes of an example. And the way this algorithm is gonna work is what we do is we actually explore all of our neighbors first. Okay, so instead of trying to go deep into the graph, we fly to everything that is close to us. All right, so this node we can fly to immediately because we're already there. So we start there, it takes 0 steps to get there. Then what we do is we visit both of these nodes because they're 1 step away. All right. Then what we do next is for all of the nodes that it's as if we were at these 2 nodes right now. For all of the nodes we can visit in 1 more step, we go visit those. All right. So that's these. So from here, in 1 step we can get here, in 1 step we can get here, and in 1 step we can get here. Does that make sense? You can imagine it as if you're flying around and you're kind of like visiting the stuff that's closest to you in a way. Closest as defined by connectivity. Another way to think about it is you can imagine like it's kind of water. Water is kind of like flowing out of this node, and first it's going to hit these, and then it's going to flow further out from that. Okay. And then you do 1 more step and you can reach this last node. So this node took 3 steps to reach. It's kind of like the furthest from us. Okay. Yeah, this again, like I said, this edge should be here. Sorry about that. Actually, maybe I can fix it. It's fine. Any questions on breadth first search? Do you guys kind of see where the name comes from? Okay, cool. And what you should notice is that this explores an entire connected component. Does that make sense to everyone? Similar to depth first search, if there is a way for me to reach you, I will reach you, right? Okay, so another thing to notice, or how would you code this algorithm up in pseudocode? How would you do this in pseudocode? Yeah. 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 So what we're going to do, what's going to be helpful actually, is we're actually going to keep track of, so this is not the way you have to do it. Again, there's a lot of different ways to implement this. We're going to keep track of the nodes that we visit at each level, in a sense. That's what we're calling this L. So the very first thing we're going to do is we're going to initialize I lists from 1 to n that are all empty. Each list is going to, or each vector, whatever you want to call it. Again, you don't have to use this to implement it, but it's going to be helpful for our discussion of the algorithm itself. The very, very first thing we do is we say, well, L0, so the nodes I can reach in 0 steps is just the node at which I started, W. Okay. Then we're going to mark W as visited. So we're going to say we've already been to you. We are completely done. Okay. And what we'll do is for each of our levels, starting at level 0 up to n-1. So for each list in our levels, right? And we're going to start with this list, L0. For every node in our list, so at the very beginning, it's going to be just for W because our list starts with just W. All right. We're going to look and grab all of the neighbors of every node in our current list, right? And if we have not yet visited that neighbor, we're going to mark V as visited, and we're going to put it in Li plus 1. Okay. This is one possible implementation of depth first search. It's 3 for loops. Okay. Does it make sense why this? Okay, so the claim is at the end of this iteration, L0 is going to have W in it. L1 is going to have these two nodes in it. L2 is going to have this node, and this node in it. And L3 is going to have this node in it. Okay, I forgot to color them in, I guess. Okay. Does that make sense to folks? Any questions? I don't see a lot of folks piping up here. We go through all the nodes in L. Yeah, we talked about this. We go through all the nodes at our current level, right? So we start at level 0 where we have just our starting node. We go through all the nodes at the current level. And for any neighbors we haven't visited, we add it to the next level. We add those to the next level, right? So I plus 1. And then once we're done with level 0, right, we're going to go back up and we're going to start on level 1. So we're going to look at all the ones that were in level 1, right? Okay. So we sort of talked about this already, but BFS will reach anything that is connected, right? So in a single connected component, you will get to every single node that you can reach. What's the running time of this algorithm? Again, the way I implement it shouldn't really matter how I implement an algorithm. Usually it'll have the same running time. But yeah. Yeah. O of n, because you visit each node once. It's very close. Can we throw m in there as well? Or yeah. O of what? O of m, yes, because you go through at most each edge, right? So yeah. Yeah, O of n plus m. Yeah. So and again, the reasoning is not like you might look at these 3 for loops and you might be like, oh, this is O of n cubed or something, right? Again, that's not true, because what happens is if you think about what the algorithm is doing, right? Even though we have 3 nested for loops, we are only ever interacting with each node once. And at most, we're crossing every single edge, right? Sometimes we actually don't even cross certain edges. Okay. So the running time to explore the graph is O of n plus m. It's a very similar argument to DFS. So actually, this algorithm has the same running time as that first search. Okay. How would you modify this algorithm so it'll work on directed graphs? So if I go back to our pseudocode, what would I change in the pseudocode so that it works for directed graphs? Yeah. Yeah, that's it. So I would change this for each v, which is an out neighbor instead of an in neighbor. So then I only follow the edges going out, right? That would be the only change I need to make. It works for directed graphs, right? Cool. Good job, guys. Again, so we are going to talk. So with DFS, we talked about a DFS tree, right? We used it to prove that DFS can help you topologically sort a directed acyclic graph. In BFS, you are also implicitly building a tree. So the edges that you take build a tree. Okay, why is this a tree? We talked about this with DFS. Yeah. Yes. This creates a tree because if we look at the pseudocode, we never go back to a node that we've already visited. So we always avoid cycles. So if you have a graph with no cycles, it is a tree. If you have a connected graph with no cycles, it is a tree. All right. So here's what the tree would look like for this example, right? So you can imagine this is our starting node. You can imagine just picking it up, and you'll notice our immediate first two children are the ones that are 1 step away. These children are the ones that are 3 steps away. And this child is the one that's 4 steps away, right? Here are the other edges that we didn't take. So we did use them to, we might have looked at the edge, but we noticed that we had already visited, right? So when we were here, we had already visited F, we had already visited D, so we don't take that edge, right? Yeah.
Why would C have the last step instead of
Yeah, this, it's because, yeah, sorry. So I fix this every time and then it just like gets unfixed. This edge is here. I like all the pictures where you've seen this edge sticking out, it's supposed to be here. I don't know why, but I think every time I like reload the page, it like moves it. I actually have had to fix it multiple times, right? So this is what the graph looks like. From A, you start, and first you visit E and B. Then from E and B, you will visit D because it's 1 away from E, and you'll visit F and C because it's 1 away from B. And then G, there's actually many possible ways you could visit it. You could have said like, oh, you know, from F I can get to G, from D I can get to G, from C I can get to G. In this example, we are picking the vertices alphabetically. So we started with C, and that visited G first, and then these just like did not because G had already been visited. Okay, but that's a great question. Apologies for the poor graphics. Cool. All right, so this tree, ignoring these edges, is what we call the BFS tree. Okay, breadth first search tree. So it's similar to the DFS tree, and it's going to have some interesting properties. So you might notice that our list L0 is the first level of the tree. Our list L1 is the second level. Our list L2 is the third level, and so on and so forth. So the lists we were creating in our pseudocode actually correspond to levels on our BFS tree. Okay. Let's try this. So who knows what a Bacon number is? Is this like am I too old? Have you guys heard of like Bacon numbers? A Sloan has. Do you want to tell the class what a Bacon number is? Huh? Oh, okay. It's been a minute. Oh my, okay. You guys are telling me I'm old. Yeah, sure. Yeah, it's a Kevin Bacon number, right? Yeah, Bacon number, Kevin Bacon number. All right.
He stopped teaching me math a while ago, so I don't remember anything.
Okay, so let's forget it's called a Bacon number. Basically, the idea is that basically what we're trying to do is essentially, if you look at movies where actors interacted in the same movie, okay, the idea what we're trying to figure out is how far away is. Okay, Siri, glad you didn't get that. Okay, how far away is Samuel L. Jackson from Kevin Bacon, right? So basically, how many movies would I have to watch? Or like, yeah, Samuel L. Jackson is in a movie with some actors, okay? Those actors could also be in a movie, in another movie with Kevin Bacon. And the Kevin Bacon number tells you how far away, like how many steps do you have to take before you get to Kevin Bacon. Okay, and the reason it became popular is because for the vast majority of actors in Hollywood, the most steps you take is like 6, because Kevin Bacon is very popular. Yeah. Yeah.
That thing they said, like everybody in the world is connected in like 7 people.
Yes, yes, yes. That is also where that comes from. So it is very true that almost you are probably at most 6 steps away from Obama, right? Like you know someone who knows someone who knows Obama. Okay. You probably do. Like, don't be surprised because you know a lot of people, right? Most people know like 50 people. And then if each of those 50 people also know 50 people, you're already 50 to the 50th power, which is like into the thousands of people. And then if each of those thousands of people know 50 people, like pretty quickly you get to like, oh, the entire population of the US, right? Which Obama is somebody, right? And he's also a very famous person. So he probably knows more than 50 people, right? Like a couple thousand people probably know or have interacted with Obama. If you guys want to know, I have never met Obama, but my brother-in-law won a presidential scholar and he got to fist bump Obama. So at least you guys are, you know me, I know my brother-in-law and he knows, he knows Obama. So, all right. But here's the exercise. How would you figure out so let's say we have a graph where each node is an actor and each edge corresponds to whether those actors appeared in the same movie. All right. Does that make that's how we're defining the graph? How would you go about figuring out what is Samuel L. Jackson's Bacon number? Huh? You go ask each actor. Okay. Well, let's assume I already have the graph. So I already asked, I didn't ask, him how far away he is from Kevin Bacon, but I asked him, hey, Samuel Jackson, who have you worked with in different movies? And he told me, this person and this person, right? Probably a lot more, but I know his neighbors. And I also know Kevin Bacon's neighbors, and I know each of these nodes' neighbors. So how might I figure out what is the distance between the two of them? Yeah.
How would you do a breadth first search from Samuel L. Jackson and choose the shortest path to Kevin Bacon?
Yep. So that is why we're learning breadth first search. So the answer, you guys probably saw this, is 2. And I believe this is still factually true today. So it turns out that one possible path, there may be others, Samuel L. Jackson and Ariana Richards were in Jurassic Park together. And then Ariana Richards and Kevin Bacon were in the movie Tremors together. And that is the closest path that I am aware of. There may be others. I don't know do you guys know of any movies where Kevin Bacon and Samuel L. Jackson were together? All right, cool. So it's actually really, really hard to find people that are 3 away from Kevin Bacon. He's like very popular, but it turns out that Oliver Sacks is one such person that has a 3 Bacon number, okay? Because in order to get from Oliver Sacks to Kevin Bacon, you have to go through Tilda Swinton. They were in the same movie when Bjork met Attenborough, which I've never watched, whatever this means. And then this girl was with James McAvoy in Narnia. And then James McAvoy was with Kevin Bacon in X-Men. Okay. So it is actually very, very hard to find these sort of people that are far removed. But again, you can imagine if you run BFS, right? This will tell you how far, if you run it from Oliver Sacks, it'll tell you how many steps everyone is from him. Shortest distance. Let's skip that. Oh, wait, what happened? Sorry. Okay, we already covered this slide. Okay, yeah, it's actually fine. I might have had a duplicate slide in there. So those are just a few examples, but basically, like we talked about, DFS can be used to topologically sort a graph. BFS has a very interesting application, which it actually tells you the shortest path between the source node where you start and every node in the graph. Okay. Yeah, and that's actually like the way we constructed the algorithm. It should be intuitively obvious to you why that's the case. But there is if you are interested in like a formal proof that walks through all the little details in the edge cases, the lecture notes have a more thorough proof as to why BFS gives you the shortest path. But for all intents and purposes, in a directed or undirected graph, where the edge weights are 1, because we're at distance 1, breadth first search is a way to get the shortest path from a single node to all of its reachable nodes. Okay. Beep boop. Yeah, so to find the distance between W and all other vertices V, what you do is you start a breadth first search at W. And then for all V in Li, the shortest path between V and W and V is going to have length I, right? So this is why it was helpful for us to define these Li sets. And then the shortest path between W and V is given by the path in the Bfs tree, which is basically the path that Bfs took. So whatever path it took is a shortest path, and the shortest path has exactly length I. Okay. If we never find V, then the distance is infinite. You can't reach it. It's impossible, right? Again, this is just an example, right? So everything that's distance 0 is in L0, which is just W itself. Everything that is exactly distance 1 is these two nodes in L1. And the path you take to them is the path that the algorithm took to get to. Okay. Here's an example of somebody that has no Bacon number. So this is Gauss. Do you guys know who he is? Yeah. I believe the Gaussian blur algorithm is named after him. Yeah. He might have been the one who, I don't know. It's hard to say invented, but probably like made it more popularized it. That's all we know. Yeah.
I remember his name from physics, like Gauss's law, but I don't think it's related.
Yeah. Yeah.
Is it the one that signaled the fastest way platinum?
Yeah, as a child. So I don't know if you guys remember from homework 0 maybe, or homework 1, when you guys were adding all the numbers from 1 to n. There's a apocryphal story that as a kid, he's the one that came up with it, because he's very smart. He was involved in physics, math, a lot of stuff. And basically he was being rude to the teacher in elementary school. And as a punishment, the teacher said, well, I just taught you how to add. I am going to punish you by forcing you to add all the numbers from 1 to 1,000,000. And that's going to take you forever because it's a lot of numbers to add. But he figured out that you can just do 1 plus 1,000,000 times 1,000,000 divided by 2. And that gives you the answer. Right. Cool. All right. What you can try is the pseudocode I gave you guys does not keep track of the distances, but you can try to think about how to modify the pseudocode so that it does keep track of the distances. So that's basically it. Okay. That is breadth first search. It's very similar to that first search. It is useful for computing distances between pairs of vertices. That means that we can find the shortest path between U and V in linear time, right? So the reason why do I write OM here? And that's still technically correct instead of O of n plus m. Yeah.
The number of nodes never surpass the number of edges.
Yes, O of m is basically O of n squared, right, at most. So yeah. Now we're going to talk about some reasons why it might be useful to have breadth first search. There is something called, there are things called bipartite graphs. Okay. So for example, let's say you have a bunch of fish and you want to put the fish into 2 tanks. Okay. Now, some pairs of fish always fight with each other. So they can't be in the same tank because they'll cause a fight. Okay. The question is, can I put fish, if I give you the set of fish and I tell you who fights with who, is it possible for me to put them into 2 tanks? How would you guys answer that interview question?
What were the rules again? College fish.
Right. So I'm going to give you, I'm going to uniquely identify the fish for you. So I'm going to have hundreds of fish, let's say. And for each pair of fish, I will tell you these pairs fight with each other, so they can't be in the same tank, or these pairs don't fight with each other. So it's okay, we can keep them. And I only have 2 tanks. And my question to you is, given these fish and given who fights with who, can I put them into the 2 tanks? Like, is there a way for me to separate the fish such that there are no fights? Yeah.
We should do, like I said, graph per search, and you just have it so you connect the fish that do fight with each other. And so then you can find whichever fish are 2 or more distances away to be together.
That's very close, actually. Yeah. So the first thing we're going to do is we're going to model this as a graph. So so again, graphs come up everywhere. Okay. So this might be the interview question you're given. They won't tell you do it as a graph, but this is an example of using graphs to solve real world problems. This is a little not super real world, but there are a lot of problems where bipartiteness comes up. So what we do is essentially we represent, each fish becomes a node in our graph. And if they fight with each other, we draw an edge between them. Okay. Now, what's going to be helpful is to define what a bipartite graph is. Have you guys heard of this before? Do you guys know what a bipartite graph? No? Okay, that's perfect. So this is what a bipartite graph looks like. Okay, this is an example of a bipartite graph. A bipartite graph is a graph that can be split into 2 sets of nodes. You can separate them such that there are no edges between set 1. So none of the blue nodes are directly connected to each other. And there are no edges between set 2. None of the yellow nodes are directly connected to each other. That is called a bipartite graph. Can you guys see why bipartite is used as the name? So 2 parts. You can split it into 2 parts, right? How might knowing this, so like, let's say I had an algorithm that could tell you a graph is bipartite or not. Does this help you solve the fish problem? How would you solve it? Yeah, Lester?
Put all the fish that would fight with each other on the same side, so they don't connect, and then all the fish that they won't fight with on the other side.
Yeah. Yeah. So you can take the graph I give you of the fish, and you can ask my magic box, my algorithm, is this bipartite? If it is, that means that it's possible to split it into 2 sets where this set has no edges. So there is no fighting between them, right? So this would be tank 1, tank 2. If it's not, then it's impossible, right? Then that's exactly what we said. So for example, in our fish example, we would put these in tank A and we would put these in tank B. And each edge represents whether they can fight or not. Another example, real world example, is another graph that comes up that is naturally bipartite is the set of students and the classes they take, right? If you define the edge as student takes class, student A takes class B, then naturally all the students don't take classes with don't take another student as a class, and all the classes don't take other classes as classes, right? So you have a bipartite graph. Is this graph bipartite? This is an example, yes, no? Yeah.
So there are like 2 lines that have both connected to anything. So I don't know what that means.
Oh, like these are not connected to anything. That's a good point that you brought that up. The definition of bipartite is that there is within this set, they have no connections to each other. And within this set, they have no connections to each other. That is the entire definition. So is this bipartite or no?
Yes.
It is, right? Does that make sense to everyone? Okay. What about this graph? Is this bipartite? Yeah, back there. Yes. Okay. Somebody thinks yes. What do you guys want to vote? Who thinks yes? Who thinks no? I see a lot of yes. Yes. Okay, how are you guys figuring out that it's bipartite? Yeah, what the colors? The colors are helping because you're basically like, here's a blue, and then I'm looking like, let me look at the neighbors. Are any of the neighbors blue? Right.
Any of the blues connected to any blue, any of the yellows connected to any yellow.
Right. That's great. That's great. Is this graph bipartite? It's actually the same graph as before. So it is bipartite, but it's a lot harder to tell because I haven't colored it. Well, these two graphs are the same, right? Except this one I gave you colors, and this one I didn't give you colors. Okay, so this is a lot harder to tell whether it's bipartite. Why? Because it doesn't have the colors, right? What about this graph? Is that graph bipartite? It's actually not. I don't know if you guys noticed, but I added an edge, and that actually makes it so that I believe it creates an odd cycle, which makes it impossible for it to be bipartite. But you can imagine, if I gave you this, if I give you this, it's pretty easy to tell. If I give you this, it's pretty easy to tell. If I give you this, it's a little harder, right? It's very hard to tell because this one is bipartite, but this one is not, right? So what about the fish one? Is this bipartite? Can I split my fish up into colors, into tanks? All right, think about that. But think about more generally, how would you be able to tell if a graph is bipartite? Yeah.
I'm thinking that you start somewhere and then you look at off the
Yeah. Breadth first search.
You go through all those children and you kind of set them, like if you had two separate camps, I guess we'll call them.
Yeah.
And the first one that we started at to one side, we add all those children to the other side.
Right.
And we check to make sure, and I feel like we have to go through this time. And then like go through the children and put them on the other side or make sure that they're not connected to the ones that already are on the side that you're trying to put it on.
Got it. Okay. Yes, that is exactly what you would do. A little easier to see without the tanks would be, well, I start at some node with BFS, and I'm going to put it in tank 1. So I'm going to color it blue. And then all of its neighbors, well, they can't be in the same tank. I only have one option. They must be yellow. So I'm going to color them yellow, right? And then I'm going to repeat that. Any neighbors of the current node, I'm going to color the opposite color. And if I can do that, right, without running into a cycle where I go into a node I've already colored and they're the same color, then you have discovered a way to partition the graph into into two parts. So for sure, it is bipartite. Now, the question you should be asking is, if I run into a cycle, does that mean it is impossible to color the graph? Or did I just do it, like what if I started with another color here? Or what if I started in this node instead, right? Like if BFS can color the graph, then it is definitely bipartite. But if it cannot color it, it's definitely not bipartite. That's a question to think about. And we're actually going to cover it. So just like you guys said, so color all the levels of the Bfs tree in alternating colors. That's the plan, okay? If you never color two connected nodes the same color, then it's bipartite. Why? I found a set for you that is blue and yellow that are not connected, right? So that should make sense to you. Otherwise, the claim is that otherwise it's not, okay? Now, skip this. Okay, I guess these are examples. Okay, let me fix this slide. Give me a second. Oh, okay, there's too many slides to fix, so you guys are just gonna have to go with it. But here's an example. Again, this edge should be here. Okay, so just keep that in mind. So if we test for bipartiteness, we can use BFS. And what we do is we color the node we're on yellow. We color its neighbors blue. We color the neighbors of its neighbors yellow. And we color those neighbors blue, right? And we never ran into an issue here, right? The only edge that is connecting, this edge is actually connecting these. They're actually opposite color. So that's okay, right? So this graph is clearly bipartite. I just gave you a partition, okay? Now this graph, you know, I do the same process. I start yellow. I go here, color those blue. I color its neighbors yellow. And now, because I have this edge, I have run into a problem. I have a yellow that's trying to connect to another yellow, right? So this doesn't seem bipartite, right? Could be two fish that fight with each other. But the question is, just because that coloring doesn't work, why does that mean it is impossible for any coloring to work? Just because I couldn't do it with this run of BFS, why does that make it impossible? Why does that mean there is no way to color that graph? There is no way to split it. This graph. So this is an example of me trying to color it, right? This is actually an example of a greedy algorithm where you, because essentially what you're doing is you're coloring it yellow, and then you're saying you're going to be yellow forever. And then I know your neighbors can't be yellow, so I'm going to try to color them blue, right? So you're greedily making decisions. And in this example, we ran into a problem, but why? What if there's another way to color it where I don't run into a problem? Or do I, like, how do you know you will always run into a problem? Yeah.
If you change one of the colors on the nodes, you have to keep changing horizontal to fit. So that like you just keep shifting it forward. So whatever. For example, if you change the orange fish,
Yeah, to blue. Yeah. Then you got to change these to yellow. Okay. Then you got to change these to blue. Oh, and now I've got a problem. Got a blue. Okay, so now you have two colorings that don't work. All right. What if instead of using BFS, I tell you I'm going to color this yellow and this blue and this yellow and this, you know, what if I try to do some other coloring that is not based on BFS? How do you know that won't work? Yeah.
Could you say maybe it has to do with like Bacon numbers? So it's like between every blue and another blue, there's only one yellow in between. And if there's two yellows, or if there's like a Bacon number that's more than two, then it means that no matter how you cover it, there's always going to be yellows connecting or like blues connecting.
I like the way you're thinking. You're very, very close. Okay, there is something about this graph. You can say it's related to Bacon numbers that makes it impossible for me to color it, for me to split it. Okay, so we're going to talk about it, right? So just because one coloring doesn't work, how do I know that no coloring works? And the basic idea is if BFS colors two neighbors the same color, then it has found a cycle of odd length. Okay, so if when I'm running breadth first search, I run into a situation where two of the neighbors are going to be the same color, then that means there is a path from my starting position to here that is odd. 1, 2, 3. Yeah. So there's a path. Wait, let's see. So there's a path from here, 1, 2, 3. That's odd, and then there's a path from here, 1, 2. That's even. So overall, this creates a cycle because I get back, right? So I can start 1, 2, 3, 4, 5, and now I'm back to the beginning, right? And the claim is that that cycle is of odd length. Why is it of odd length? How do I know it's definitely odd? The what? Most
amount of steps it takes. So I can replace that.
Yeah, it has to do with the steps, right? So in order for these two nodes, in order for BFS to try to color them the same color, right? that means, so every node that's blue is going to be an odd number of steps away from me, right? Because 1 step it's blue, 2 steps they're going to try to be yellow, 3 steps they're going to try to be blue, right? So that means that for this one to be yellow, aka the same color as me, the number of steps here must be even, right? Now for this one to be yellow, right, the number of steps here must be even. And if they're connected, even plus 1 is odd. So there is a cycle that is of odd length, all right? Now, because, okay, and now you can actually forget. So if I have a graph that has a cycle of odd length, why does that make it impossible for any coloring to work? Yeah. Yeah, you can actually work this out, but it's just like, you can forget the rest of the graph. You can forget everything else you've seen. As long as you have that one cycle, that cycle itself is impossible to color in a way where you can split it up. Because there's an odd number of vertices and they all connect, like the next one connects to the next one. So no matter how you try to split them up, there will always be an edge between 2 of the groups, or like within 2 of the groups, within the 2 groups. Okay. Yeah, so that's it. You can never color an odd cycle with 2 colors so that no 2 neighbors have the same color. Yeah, I encourage you guys to like practice, like test that out, but that's a far easier problem than just looking at a graph. So the argument we're making is, if BFS runs into a situation where it's trying to color 2 nodes the same color, then the path that those nodes make, the cycle that BFS makes, is going to have an odd number of nodes, and it is impossible to color an odd cycle. Okay, cool. Which means you can't legitimately color the whole graph either, right? If you have some nodes you can't color, then you can't color the whole graph. Thus, it's not bipartite. So you have learned that you can use BFS to detect if a graph is bipartite or not, which means you can solve our fish problem with BFS. And I think this is the separation that actually works out. So it is true that the graph is bipartite, and you can split the fish into 2 tanks where nobody fights with each other. Okay, this is called the 2 coloring problem. There is an interesting extension of this called the 3 coloring problem, which is, can you split a graph into 3 different sets where there are no edges within each set? It's a lot harder. Cool. So again, let's recap. So on Friday, we covered graphs and depth first search. Monday, we covered the applications of depth first search. So you should know that you can use depth first search to topologically sort a graph, which actually tells you the dependencies in which order you need to install things, for example. And then what we covered today is we actually covered that BFS. Okay, well, another thing, we didn't really cover this last lecture, but you can use depth first search to print out things in order. So if you guys remember, we had when we covered trees, we talked about how you can print out the sorted nodes in order when you had BSTs. Now for breadth first search, the most obvious application is you can use it to find the shortest path between your node and every other node. Okay. Another application is you can actually use it to figure out if a graph is bipartite. You can also use depth first search to figure out if a graph is bipartite. You should think about that. Cool. So, wow, I have a lot of duplicate slides. My bad. What we're still going to cover in the next few lectures is using BFS or DFS, we can find connected components of graphs. We're going to introduce something called strongly connected components, which means there is a path from every node to every other node. Okay, and we're going to talk about how to solve that. That's actually going to be next lecture. And we are also going to start talking about how to find the shortest path in graphs where the edges aren't 1. So we're going to introduce weighted graphs where the edges can have different weights, right? And then that's it. That's it. That's it for today. You guys are done. You covered breadth first search. You now know how that works. All right, thanks for coming, folks. I'm going to stop the Zoom. And yeah, just remember your midterm is coming up. So please start studying for that. All right, thanks everyone on Zoom. I'm gonna jump off now. See you guys.